Now, I've got some explaining to do. So over I'd say the entire course of parts 1 and 2, we kept having to put off this rather uncomfortable fact that everything we were deriving seems to require this one matrix to be invertible. And I said, just wait, that's a loose end we'll tie up. And I want to provide some justification for why that's true. It turns out that the full proof of some aspects of this is clever, but not actually that exciting, and you don't learn much from it. But certainly I need to make sure I explain why we can reasonably assume that in the context that we're using it in this linear algebraic simplex method, that matrix, the basis matrix, is invertible. So to recap, recall that I keep using this inverse of AB everywhere. So if we take a look in the pseudocode from the end of part 2, let's see. Make sure I'm not missing anything. I need to use it 4 times. And while I'm iterating, so while in the process of pivoting during the main body of the simplex algorithm, I need to compute the inverse of the matrix AB and use it twice in each iteration. So certainly if it were to become the case that AB is not invertible, the algorithm would fall apart. So all of that derivation we spent 2 hours on would be for nothing. So certainly it's a big deal that we can justify why this matrix is going to be invertible. So we have to talk about this. We can start by trying to take the easy road. So we know that the matrix AB is a collection of columns. It's a subset of the columns of this larger matrix A. So maybe we could show that if you pull out m columns from it, so remember that AB is it's an m by m matrix. If I pull out any m columns from A, am I guaranteed that the result will be invertible? If I could show that, then my work is done, because that way there's no possible way that AB could ever not be invertible. The problem is the answer to that question is in fact no. So it turns out, even in the LP we've been working with this whole time, sort of my running example of an LP, I can show you an alleged basis for which AB is not invertible. So here it is. Here's my matrix, my big matrix A, and I say, suppose I tell you that the basis is x2, x4, x5. If I do this and you go pull out those columns to form the matrix AB, you get this. And notice that, quite conveniently for proving this point, it even has that telltale row of all zeros. So we know already that, hopefully, I assume you know from linear algebra, if you have a row of all zeros in your matrix is definitely not invertible. And there's lots of easy ways to justify that. One of them is you could think about what the determinant would look like. There's no way the determinant, if you consider a cofactor expansion across this row, there's no way that determinant's not going to be 0. You could also consider linear independence, and you know that, of course, the 0 vector is not linearly independent from these things. And so there are a few options there. In any case, that matrix is definitely not invertible. Now, to be clear, it doesn't necessarily have to have a row of all zeros to not be invertible. So there could be other choices of basis where AB isn't immediately, it may not be invertible, but that's not immediately obvious, but it still isn't. So obviously, you hopefully are familiar with the fact that a matrix can be non-invertible despite looking very friendly and potentially looking like it's invertible. So what this has shown is that clearly it's not just a matter of yanking out any 3 columns and that gives us an invertible matrix. What we therefore can hope to do is at least show that all of the matrices A, B that we are likely to see, and in the context of the simplex method, that would be the matrices corresponding to a feasible basis. We need to at least show that all of those are going to be invertible, and that is something that we can do. And one way of demonstrating that point is, instead of going directly towards that, let's try and explore what went wrong with this example. So this is a bit unsettling. Obviously, it would have been great if we could show that any 3 columns of this matrix A produce some invertible matrix, but that's clearly not the case. So to avoid being disheartened, let's go back to that old standby. Let's think about what would happen in the dictionary-based method with this basis. Is this a real basis? Am I allowed to work with this at all? And so maybe I could do an experiment and try and figure out what's gone wrong here. Like, what would I do with x2, x4, x5 in a dictionary? So here is the initial dictionary for the same LP. And what I want to ask about is, what happens if I have the basis x2, x4, x5? So what I want is to put x2 in the basis. And you'll notice x4 and x5 are already there. So clearly the only way of getting x2 in the basis is to pivot out x6. So I wanted to pivot with x6 leaving and x2 entering. And I stare at it for a minute and I realize that in fact, I can't. In the dictionary-based method, the basis x2, x4, x5 is also invalid because the pivot I would have to do to get x2 into the basis is impossible. There's no way to perform this pivot because I'd have to divide by 0. So in a sense, that's a little bit reassuring because we know the dictionary-based method works. We went through that in great detail, proving that that works. And that means that the fact that there was this one apparent basis that wouldn't work with our linear algebraic method isn't as big of a deal if we know that it also doesn't work in the dictionary method. It also makes it a bit more concrete exactly why the matrix wasn't invertible. Because if we think about it in terms of individual pivots, the pivot that we would have to perform is impossible because we can't divide by 0. So this does give us some hope and also allows us to refocus our efforts on proving that if I'm working only with a feasible basis, although it turns out there are bases that aren't feasible, for example, even dual feasible, but certainly there are bases that are neither dual nor primal feasible that can exist where the matrix happens to be invertible. For the sake of the algorithm, all we really have to show is that the matrix AB that we're actually going to get in practice is going to be invertible. So we'll focus on that. And this is, so this is just saying we don't really have to address the general case, just the case where only the case of the matrix AB that we're going to actually see while running the simplex method. So the question is, can we show if I start the simplex method from a feasible basis, so putting aside for a moment whether the current basis gives me an invertible matrix, is it true that if I start with AB being invertible and I do a pivot, that the resulting matrix will also be invertible? And the answer to that is yes. I'm going to talk about why that is in a minute, but there is a full mathematical proof of that in one of our books, in this book. The proof itself is neat, but it isn't really that relevant to the course. It is mostly housekeeping. I mean, there's some neat linear algebra that they're doing in there, but it's not that exciting, not worth spending 20 minutes on in this video. But there is a proof. If you want to look at it in great detail, there it is. I want to talk about the justification. So what I'm going to give is sort of Van der Bee's version of the same explanation, although Van der Bee doesn't give this a full algebraic proof like the other book does. And we can use the dictionary form to justify that. So suppose I perform a pivot in the dictionary form. I started with a dictionary, a basis that's feasible, and I perform some kind of a pivot. Any pivot operation, fundamentally, really is actually an elementary row operation. So at the very beginning, I mentioned this, that secretly, deep down, my dictionary-based simplex method was actually doing the same operations as Gaussian elimination. And maybe you know that if I have an invertible matrix and I perform some elementary row operation, the result is also invertible. The reason for that is because any elementary row operation performed on a matrix is equivalent to multiplying that matrix by some invertible matrix. And of course, if I multiply two invertible matrices together, the result is also invertible. Another, I think, more intuitive way of thinking about it is that we can reverse any pivot operation. If I were to pivot, let's say with x3 entering and x6 leaving, the dictionary I end up at I could always reverse that pivot operation by simply putting x3, taking it back out of the basis, putting x6 back in the basis. In general, if I pivot with xj entering and xi leaving, and then I get to the next dictionary, I can always recover the dictionary by then having xi enter and xj leave. And so because every pivot operation is reversible, in a sense, that is the definition of invertibility. If I perform some operation on a matrix that's invertible, and the operation itself is reversible, then the operation can be inverted, and that means the product of that operation and my original invertible matrix is itself invertible. So that's the idea. That's the intuition behind this. If I start with something invertible and I perform a pivot, any valid pivot that I can perform, so in this dictionary it's any pivot except for this one, which I can't do, any valid pivot is reversible, and therefore if I started with invertibility, I maintain invertibility. On the other hand, you should be asking, okay, so what we've just shown and what this other proof that I referred to shows and proves mathematically is that if we have an invertible AB and I do a pivot, the resulting AB is also invertible. But of course, there's a bit of a chicken and egg problem there, which is what about the matrix that I start with? What about my initial basis? And basically the answer is, well, if the LP was initially feasible, what does the initial basis look like? Well, we know that if the LP is initially feasible, our initial basis will just be the slack variables, just like how in dictionary form we are used to our initial basis being all the W's. And then we ask the question, wait a minute, what does the submatrix of my equational form look like for the slack variables? Remember that A, the equational form matrix A, is the original constraint matrix you gave me from standard form, and that corresponds to all of the optimization variables. So that would be x1 up to xn. And then I define my slack variables xn plus 1 up to m plus n. Maybe I should call that n plus m. And those columns are just an identity matrix. And we think, wait a minute, that means that if my LP was initially feasible, then the initial basis, the initial matrix AB will just be this thing. And if this is an identity matrix, obviously that's invertible. Okay, so there's that. Now there's one other piece to the puzzle, which we're going to get to a little bit later in this lecture, which is, wait a minute, you said initially feasible LPs. What about LPs that aren't initially feasible? And the answer for that is, what we'll see later is that using a primal dual, a two-phase method, we can find a feasible point, a feasible basis for any feasible LP that isn't initially feasible. We can find a feasible basis by solving using a two-phase method where the initial phase uses exactly the same constraint matrix A. So all of the same properties apply to it. And in the initial phase, we work with a problem that is initially feasible. That means this logic applies to that as well. And because we start from an initially feasible problem and then we do a bunch of pivots which preserve invertibility, the basis we end up at the end of our first phase, because it's on the same constraint matrix that we're working with in the second phase, if that basis was an invertible matrix, which this point and the previous one both together, taken together, require, then the whatever dictionary we start with, whatever basis we start with in our second phase, that will also have an invertible matrix AB. And actually, when I post the slides, I think I'm going to add a bit more text here to describe the argument that I just made. Now, we should also talk a bit philosophically about this word that I keep using. So what have I been doing all along? Well, I had this big matrix A. So A was this, in equational form, this large matrix that has m, maybe I'll write m columns, or no, sorry, not m columns, m rows, and m plus n columns. And I yank out some selection of columns from this, and I end up with this matrix AB, which is square. And it will have m rows and m columns. What I have proven is that for any feasible basis, this matrix here will be invertible. And it turns out we can say the same thing about dual feasibility, as we'll see in a few minutes, because it turns out that for something to be dual feasible, we actually still work with the matrix AB defined in the same way. And so it turns out that if it's invertible, it'll be invertible in any case, dual feasible or primal feasible. So this matrix AB has m rows and m columns, and it is invertible. So maybe you know already that the fact that AB is invertible is equivalent to the statement that AB has full rank. And we know that the rank of the maximum rank that AB can have is m, because it's an m by m matrix. It's a square matrix. That means that the rank of AB has to be m, has to equal m. It's also a fact that the rank of A has to be at least equal to the rank of some subset of its columns. And so that means that the rank of A has to be greater than or equal to the rank of AB, which in turn implies that the rank of A has to equal M if there is a feasible basis. And it turns out that there's actually, it's not only true for that case, if there's any feasible basis-like thing, dual feasible or primal feasible, it might be true otherwise too, if there is a feasible basis. In other words, if there is at least one AB that's invertible, that means that the rank of A has to equal M. And the reason why this is significant is if we think back to what we're actually doing here. So I've taken a bunch of columns out of A, made up this new matrix, shown that this matrix AB is invertible, that is to say it has rank M. And then, of course, by extension, that means that A is invertible, or not invertible, A has rank M. But it's true then that whatever columns I used to build AB, they together can generate some subspace of dimension M. They can generate the column space of A. And that means that those columns, the columns of AB, are in fact a linear algebraic basis for the column space of A. And that, finally, after 2.5 months of talking about this, finally we understand why we've been calling it a basis. All along, hidden deep down under all these layers of algebra, from working with this dictionary form where it may not have been obvious, it turns out that the reason we call the basis a basis is because those columns of my equational form matrix are in fact a basis for the column space of that matrix. That's where the word comes from. That's why it's a sensible term to use. Now let's talk about the dual simplex method. So the dual simplex method can be done linear algebraically as well. That should surprise us in absolutely no way, because we understand if the primal simplex method can, of course the dual simplex method can. I would like to present the dual simplex method in linear algebraic terms using the same notation as the primal simplex method. In other words, I'm going to use the same equational form for both. That means that my derivation of the dual simplex method, just like earlier when we talked about the dual dictionary, so we saw earlier, this is the sort of pseudo-dictionary for the linear algebraic dual simplex method. This looks quite a bit uglier in some ways than, this should be an XC. This looks quite a bit uglier in some ways than the primal pseudo-dictionary. And I mentioned earlier, the reason for that was because we started with the equational form derived from the primal problem, and that required us to adjust some things. On the other hand, we can still derive the dual simplex method from this whole thing. One thing we're going to observe is when I talk about this, it's going to be a bit more confusing than usual. I imagine it's probably already pretty confusing, especially 2.5 hours in. It's going to be more confusing than usual because remember that when we talk about the dual simplex method, we talk about it using the terminology of the primal dictionary. So when I go to choose a pivot in my dual simplex method, I will choose a pivot using my vector xb. The basic variables of the primal dictionary, of course, correspond to the non-basic part of the dual dictionary. Additionally, because I want to use only the terminology of the primal dictionary, the thing I choose, sort of the column I choose in the dual dictionary that would be considered sort of entering in the dual sense, we're going to be calling that the leaving variable. Because in the primal context, again, these are the basic variables in the primal dictionary. So we're going to call what we choose here as our pivot the leaving variable, and what we choose over here as our entering variable. We're going to use the terms of a primal pivot to describe this thing when we talk about the dual simplex method. So besides the obvious transposition, which is to say that we're going to use the vector x in the dual method the way we use the vector z in the primal method, besides that, it turns out there is a pretty ugly change we have to make down here. It is the analog of what we had to do back in the primal method with that weird sort of word salad explanation of how where we had to worry about this product an xn and show that it equaled, for a particular entering variable xj, it ended up equaling this thing. We might recall that was a bit of a trying explanation, and unfortunately, we can't even use that trick in the dual version. We end up with something even more complicated there. So other than that step, I'm not going to describe most of this in very much detail because I feel like it is symmetric in a lot of ways to the primal case. Okay, actually, before I do that, one more thing. So just like we saw, step 1 is pretty similar to the primal method, except I'm obviously using different variables. So I'm computing this, which corresponds in some way to my objective coefficients. And just like before, if I end up observing that xb is greater than or equal to 0, what that's saying is I've got a primal feasible dictionary. And if I'm running the dual simplex method, I'm assuming it's also dual feasible. So that means that I have primal feasibility and dual feasibility. That means that we're done. That means we have an optimal solution. Notice that, as we expect, the objective value, negative c, will be this, which is exactly the same computation as the primal objective value. We, of course, expect that from the negative transpose property, and we expect that as reinforcement of that wonderful beauty of duality in general. So let's walk through the rest of it. So first, I choose a leaving variable. Notice how in the dual simplex method, we consider that we choose the leaving variable first. So I'm choosing a leaving variable from among the basic variables. What I'm really doing, of course, is examining my dual objective coefficients and choosing my leaving variable based on those. Just like in the primal method, that means inspecting this, what amounts to a coefficient vector, and looking for negative elements. So I do that. And of course, the choice depends on the pivot rule as usual. Oh, and of course, the leaving variable is not an x variable, it's a z variable, because I'm working in the dual problem. Then we have to deal with this. So we have, if we look at the primal dictionary, just like how we dealt with this, if we look at the dual dictionary, just like how we dealt with this with the primal dictionary, we have to figure out, if I've chosen a variable to pivot from among these, I now have to figure out which of these things it places the tightest bound on. Notice that we have a bit of more of an uphill climb here, because not only is this something different, it's got a transpose on it that's going to make our lives a bit harder. Also, it's been sort of weird, sort of arbitrarily double negated. That is a product of our derivation. We sort of had no choice but to do that because we wanted a derivation that was congruent to our primal version. That's going to make our algebra even more messy this time. So we'll try the derivation we did before. So remember that what I want is something similar to the what we had in the primal case, which is I want to say, well, if I choose a certain, in this case, leaving variable, the new values for the variables, my basic dual variables, Zn, will be something like Zn minus, we'll call it S, times delta Zn. That's what we, sort of analogous to what we had in the primal case. So what I need there is to figure out what the vector Zn, delta Zn is, just like I did in the primal case. The trick we used in the primal case doesn't really apply here, and I can explain why that is. So in the primal case, we concerned ourselves with this product here, ANXN. And I made the observation that if I'm only increasing one of my non-basic variables, xn will only have one non-zero entry. That means that the product ANXN will just be one particular column of AN. And because AN was computed by just yanking out individual columns of A, I could then reduce it down to basically, if my entering variable is xj, it'll just be the column AJ times whatever new value I have for xj. I can't do that here. This is the product I have to work with in this case, which you can see this is not a very friendly thing to deal with. AB transpose inverse. Ugh. So what I'm ultimately doing is the same, though. I'm only one of the values. If I choose to increase my choice of leaving variable to some non-zero value, only one thing in this vector is going to end up being non-zero. That isn't the problem. The problem is that, okay, if only one thing in the vector is non-zero, then the result of this product here, so A, B, transpose inverse ZB, only one thing in this product, this whole product is only going to be one column of this matrix. The problem is, unlike in the primal case, this matrix doesn't appear anywhere else. It's sort of synthetic. I have to take my AB, transpose, and then invert it. So I can't say, oh, just go pull out a specific column of A. It doesn't work that way. So instead, I have to live with this. So in the dual case, what that means I do is I actually have to compute this matrix. And notice how, so AB transpose inverse is the same as AB inverse transpose. But I mean, in any case, I have to somehow have this on hand. I would have it on hand anyway. So I would have AB inverse around because I'm likely going to be using it for other things. But because I have to do this, what I want to do is find a way of simplifying the calculation at least so that I can say, look, if my basic dual variables will end up having the following values. So something like this, separating it out, getting some vector delta Zn that corresponds to the unit change in my basic dual variables if I modify my leaving variable, so that I can keep the actual value of my leaving variable outside. So here's what I'm going to do. I'm going to basically rewrite the vector ZB. I'm going to rewrite it like this. I'm going to write ZB, which in this case is going to equal something like this, 0, 0, and then one value that's non-zero, and then a bunch of other zeros. I'm going to rewrite this as S times a vector U. And I'm going to define U to basically just be a bunch of zeros and a 1 in the position that I'm about to change. So that's all I'm actually doing. And I have to construct it with sort of weasel words, because remember that we don't necessarily know, if I know that my leaving variable is, let's say, Z5, I don't know which index of ZB that's going to be. I know which index of the big Z it's going to be, but maybe Z5 is the first index of ZB. That's why I have to use sort of vague language in this definition. So what I'm going to do is I'm going to construct a vector U defined like this. So U is the same size as ZB, and so it does, I mean, this relationship does hold. The difference is I have to be careful how I define indices. So I've chosen my leaving variable Zi. I don't know exactly which index of ZB from staring at it. I mean, implementation-wise, I would know this. I don't know which index of ZB corresponds to my leaving variable. So we'll just construct u to have a 1 in whatever position of zb has that leaving variable. That's all this is really saying. And the reason I'm doing it this way, by defining this strange vector u, is that allows me to keep the actual amount that I'm increasing my leaving variable, zi, that allows me to keep it separate. I don't want to have that included in the vector. I want to keep it separate because it'll help me compute those ratios later. So I know there's a lot to digest there. When you see the pseudocode, it might make a little bit more sense. Okay, so now here's where I try and bring the derivation back in parallel with the primal one. I define my vector delta z, and again, just like before, there are some variables that make no difference to me, so I'll just define them to equal 0, and then I define delta zn to be this thing. And if we compare this term with what we had on the previous slide, which is this, all this really is, this ends up, if all goes well, this ends up just equaling s delta zn. So all I've done is I've pulled out the actual increase, the actual magnitude of my leaving variable, and I've packaged everything else into delta zn. I'm realizing now that there is also a sign flip there. So again, we're used to arbitrary sign flips by now. The reason I put the sign flip in there is because then we get this very familiar looking invariant. Here is what I want. I need to make sure that any modification I make to my leaving variable preserves this, that nothing goes negative. Okay, so just like before, we now get back on track. Just like before, the largest amount that I can increase my my leaving variable will be defined by this. And this is where this is now matching up with our primal case again. Notice that just like before, in our primal case, the indexing I'm using is the absolute index of each z variable, so the actual z, not zn or zb. Although I'm only iterating over the non-basic, well, primally non-basic, dual basic variables, and like before, I'm only looking at cases where delta z is greater than 0. All right, so then I choose, in the event that this is empty, so in the event that the min function has no arguments because every element of delta z is less than or equal to 0, in that case, we know that the dual problem is unbounded, just like in the primal case. And of course, if the dual problem is unbounded, then by weak duality, that implies that the primal problem is completely infeasible. And so we're done in that case. Otherwise, we choose our entering variable just like we normally would. So if there are ties for variables that realize this ratio, then we use the pivot selection rule to break the tie. And then finally, we perform our pivot. And the only real difference between performing the pivot in the dual sense and the primal sense, of course, is that we're updating a vector z instead of a vector x, because the vector x is updated or recomputed up here in step 1. And so I'm not going to spend too much time on this. It's just the symmetric case of what we saw in part 2. And so here is pseudocode for the dual simplex method. So again, you hand me the equational form a, b, and c, you hand me a feasible basis, and then everything else pretty much works congruently. So there's my initial step to compute the initial values of z, because I just want to update them at each iteration. And then I start my iterative process. I compute my dual objective row, and I check for optimality. So if I discover that I have a primal feasible solution, given that I'm already working with dual feasible cases, then I have an optimal dictionary. And whoops, this should be, I'll fix this in the posted version. This should be negative xc. That's the best you're going to get for an xc today. And then I choose my leaving variable, pretty much congruent to the primal case. The only real difference in the dual case is this, that weird vector u. And remember that I could have done the same trick in the primal case, but we found a way around that made it a little bit more palatable by observing, because we don't need an inverse, I was able to just go pull a specific column out of A. I can't do that here because of that sort of slight asymmetry between primal and dual pseudo-dictionary. As a result, I have to construct this vector u, which I described back here. And then things proceed pretty much similar to the primal case. And so if I look for unboundedness like I did in the primal case, of course, dual unboundedness implies primal infeasibility. We know about duality by now. That was a different lecture. And then everything else pretty much, again, pretty much is the same as the primal case, but flipped with z's instead of x's. So there is the dual simplex method via linear algebra, very congruent to the primal one. If you take a look at Vanderbee's pseudocode, he's written it out in such a way that you can actually see that the primal and dual ones are, like, he's written it out in a way that completely illustrates that duality, whereas I've tried to condense it a bit and treat each method a little bit separately in cases where they do tend to diverge a bit. So where does this leave us? So we've just spent 3 parts and 2.5 hours deriving the full linear algebraic form of the simplex algorithm. And long, long ago, at the beginning of part 1, I said something about how this lecture was about something called the revised simplex method. And I said, maybe, this was back at the beginning of part 1, maybe we'll get there around like, what, slide 92 or something. And evidently, we've gotten to slide 98 and we're still not there. It's because I've between parts 1 and 3, I've had to add a bunch of slides. What we derived was just the regular simplex method. However, by doing it this way, by representing it using linear algebra, maybe now we can hack into it and optimize some things away. We can save ourselves some time. In particular, frankly, the most controversial thing that we've been doing this whole time is computing this matrix inverse, working with AB inverse, and also things that are pretty much the same as that require the same amount of work as AB inverse. Maybe we can find a way of not having to explicitly compute a matrix inverse, which is problematic for a couple of different reasons. Before we do that, let's talk about how, now that we have these 2 pieces of pseudocode, how do we actually solve LPs? So I guess we can take it for granted that I have to turn any LP you give me into equational form. Sorry about that, I just dropped something on the floor. I have to turn any LP into equational form before I can solve it. But what about cases where, for example, the LP is not initially feasible? And this is where the particular work distribution that we've come up with is actually very beneficial. So what's the point of a 2-phase method? If my LP is not initially feasible, what is it that I want? Well, we know from back with the dictionary-based method, if we don't have an initially feasible LP, we have a couple of options. We can use duality, we can solve an auxiliary problem, but the ultimate goal is to arrive at a basis that is feasible. I just need to find a feasible basis. And then with the dictionary-based method, I have to sort of adapt my dictionary for that new basis. One interesting thing about these linear algebraic methods is you can start them from any basis you want by just handing over the indices of that basis. That means that if I have an initially infeasible LP, and I find some way of finding the indices of a feasible basis, that by itself is enough to start up the simplex method. So the question is, how do we solve LPs in general using these linear algebraic representations? So given an LP that's already in equational form, because we know by now that's something we can easily put it into, how do we solve it? Here is my suggestion, this 3-step process. If the LP is feasible, which we can determine by inspection, if the LP is, primal feasible, I really should have said that here because I'm talking about dual feasibility on the next line. If the LP is primal feasible, which is to say if B is greater than or equal to 0, then we're already all set. We just call primal simplex, the pseudocode from the end of part 2, with my optimization variables non-basic and my slack variables basic. And we know that that means that our initial matrix AB will be an identity matrix, which of course is invertible. And then because we know that starting from an invertible matrix and doing a pivot keeps us at invertibility, we know everything's going to work out. Okay, but suppose it isn't, because we know that it's very easy to have an LP that is not initially primal feasible. Okay, so second try. If the LP happens to be dual feasible, which is to say if it happens to be the case that C is non-positive, well, in that case, that's sort of a freebie because that means that we're looking at a dual feasible LP, so just call the dual simplex method. Again, same story. Non-basic variables will be the optimization variables, the basic variables will be the slack variables. And all of the logic about AB that I talked about in this step still applies. If we go back and look at this pseudocode, notice that because I've used the primal interpretation of the basic and non-basic variables while deriving the dual simplex method, the matrix AB is the same matrix I was working with in the primal method. So any claim I could make about whether that matrix is invertible in the primal simplex method still applies here. So if it happens that my LP is dual feasible but not primal feasible, then I can just run the dual simplex method on it. But really, and when we talk about solving initially infeasible problems, we shouldn't expect that. That's just a freebie. Suppose that the LP is neither primal feasible nor dual feasible. What do we do then? Okay, so here's where we can use a really clever trick. I mentioned this at the end of the duality lecture, but it wasn't as obvious how clever it was there as it is here. It's really convenient here. And the reason is because we just pass in this equational form to these functions I've come up with. So what we do is we observe that so suppose this LP is neither primal nor dual feasible. What about this LP? Maximize, just the scalar value 0. Maximize the scalar value 0, which is equal to 0.x. or even better, I guess the zero vector transpose times x. Is this problem dual feasible? Absolutely. Because for dual feasibility, all we need is for the vector c, the coefficients of the original objective function, to be non-positive, and that's definitely the case. Which means this is definitely always dual feasible. And notice that if I were to find a primal feasible basis for this LP, it would definitely be feasible for this constraint system, which is the same constraint system as the original LP. So if I can solve this problem, which I know to be dual feasible, I can then pull out the basis that I end up at, because we know that the solution using the dual simplex method, the optimal solution using dual simplex, will be both primal and dual feasible. We can recycle the basis of the optimal dictionary solved by the dual simplex method and use that as a feasible basis for the original LP. So that's this third case here. If the LP is initially neither primal nor dual feasible, do the following. First, call the dual simplex solver using a fake zero objective vector. And as before, set your non-basic variables to be the optimization variables and your basic variables to be the slack variables. We know that that means that our initial matrix AB is invertible because it'll be an identity matrix. And we also are guaranteed that this is a dual feasible LP. This new modified LP with a zero objective function is dual feasible. We run the dual simplex method, and then we figure out when it gets to its optimal solution, which is guaranteed by duality to be both primal and dual feasible for this LP, this modified one, we then take the basis that it came up with. So we'll call those B prime and N prime. Those are the basis and the basic and non-basic variable sets for the solution to this phase 1 LP. We're guaranteed that that is primal feasible for this LP, and we know that because it's the same constraint system, it will be a feasible basis, although it may not be optimal, to my original LP. And so I take that basis, and then I call the primal simplex method on it. So if I have both primal and dual simplex implemented, I can now solve any LP that is feasible. I guess I can solve it in any case. I can decide if it's optimal, unbounded, or infeasible if I have both the primal and dual simplex method implemented. And notice also how convenient that is. Notice that if I solved an auxiliary problem with omega or something, I would then have to find a way of shoehorning in, so deleting the variable omega and then rearranging stuff like in dictionary form. But here, I call the dual simplex solver, and I just find some way of determining what basis it was working with at the end. Just those sets of indices. And I just pass them right into the primal simplex method. That's it. The turnaround between the two phases is now basically trivial. So I now have a way, using my linear algebraic solvers, to solve any LP. The question then is, what can we do with this? So we were sort of comfortable after 2 months of working with it with just using the dictionary-based method. What have I actually achieved besides spending 3 hours pontificating about linear algebra, which frankly, as an aside, in my books, I still consider a success? Well, one of them is by breaking things down using linear algebra notation, we can now begin borrowing techniques from the world of numerical linear algebra, because there are lots of numerical techniques for example, solving systems of equations, or for inverting a matrix, although we're going to see shortly we'd rather not invert a matrix if we can avoid it. So we now have this representation that allows us to easily bring in results from linear algebra and numerical linear algebra. So if I take a look at a computation like this, so here's a calculation that says multiply a vector v by the inverse of a matrix M, and then store the result in U. This is a bad idea for lots of reasons, one of which is computing a matrix inverse takes a long time, especially if I only need to do one thing with it. I need to compute the inverse and then just multiply it by one vector. So I'm inverting an entire matrix, even though my calculation is only going to produce a single vector as output. What I could do, though, is I could rewrite this. I could say, well, wait, let's multiply both sides by m, and then I go back to this form. So what I'm saying is I would like a vector u that satisfies this system of equations, m times u equals v. Instead of computing u by multiplying v by m inverse, I could just use, for example, Gaussian elimination or some other numerical technique to solve this system of linear equations. just directly. I don't bother computing an inverse. Okay, so why is that a good idea? Okay, the first thing is I'm going to use the word asymptotically, but I can't use big O notation because the constant is significant, and we know that big O notation discards that. Even if I just consider the number of calculations, I should expect that a numerical solution to this equation, computing u this way, requires n cubed over 3 operations. Asymptotically. So that is to say, as we allow n to become arbitrarily large, the number of operations sort of asymptotically approaches this thing. If I want to compute m inverse, it requires n cubed. And then I have to multiply m inverse by v, which requires n squared, although asymptotically that would go away. Asymptotically, it would just go to n cubed. So clearly, that means asymptotically, it is faster. It requires fewer operations to solve this system than it would to compute m inverse and multiply it by v. That's one reason. So from a very practical standpoint, I can save time. The other reason is that in a numerical analysis sense, this is not a numerical analysis course, but you might have taken one, computing and using inverse matrices is considered to be a very bad idea. So computing an inverse matrix in full, explicitly computing it, often will produce a lot more numerical trouble, so it could exhibit numerical instability, a lot more than just solving a system of equations. Or more broadly speaking, it's true that there are some systems of equations I could solve where the particular choice of vector v results in some bad stuff happening, but it depends on which vector v I'm working with. If I compute my matrix inverse, the numerical stuff could come up even if the vector v that I'm multiplying it by isn't going to be a problem. And so it turns out, if you ask a numerical analyst, and I actually went and did this for the sake of making this lecture back in, I think, April, I looked this up in a few places and talked to some people just to verify what I was remembering, make sure that was definitely true. It actually happens to be the case that even if I were to hand you m inverse, if I said, I need you to give me a vector u that satisfies the system of equations m times u equals v. And as it happens, I just hand over, I say, here's m inverse. I've already computed it. Go ahead and use it if you want to. Even if I hand it to you, it turns out it's still safer to solve the system of equations. It turns out that inverse matrix can be dangerous numerically. And because if you're working with floating point computations, that's something you really have to consider, because often, if our linear programs are massive, we don't want numerical errors to cause some sort of false positive or false negative situation. Even if you have the inverse already lying around, it's still a better idea numerically to solve a system of equations to compute your vector u in this case. And so what we can do then is we can work backwards from what we have. So here in the primal algorithm are all the places where we need an inverse matrix. We can work backwards from that using those insights to find a way of never actually computing an inverse matrix. So what I could do, for example, is to do this step. If I want to compute the initial value of x, or xb in this case, which is part of x, instead of computing xb to be equal to ab inverse times b, I could just solve this system of equations. The system of equations ab xb equals b. I just solved that for x using Gaussian elimination or something similar. I keep saying Gaussian elimination because those of you that haven't taken numerical analysis, I don't want to just start name dropping a bunch of algorithms or things. I'll do that in a minute, but I want to use terms that you might recognize. So I solved this system of equations to compute xb. If I want to compute zn, which is a bit more complicated, you can see there's a lot of stuff going on there, I can compute it in a couple of steps. So the first thing I compute is I will compute, actually, I'm just gonna rewrite this because I don't think it's as obvious what I'm really doing here. So AB inverse AN transpose all times CB minus CN. What I wanna do is peel away a layer of brackets. So that actually ends up equaling AN, whoops, the transpose is on the outside. AN transpose times AB, oh boy, AB inverse transpose times CB minus CN. So what I've done here is I've just split up the contents of this big transpose thing inside the brackets, just to make it more obvious where I'm getting this stuff from. So notice that what I want is first to compute this, and then subtract Cn from the result. Okay, so instead of setting Zn, where I use this inverse calculation, what I could do is I could solve the system of equations AB transpose times V equals CB. And that would give me a vector v that is equal to this thing. And notice that happens so that this would be v here. All right. And then if I want to compute Zn, I then compute An times V minus Cn. An transpose times V. That's what's happening. I'm doing it in 2 steps, but actually I'm only solving one system of equations. I'm just solving the system AB transpose V equals CB, and then plugging the V that I get from that into the equation where this inverse calculation would otherwise be necessary. Similarly, to compute delta XB, which would normally be computed this way, I just solve the system of equations AB times delta XB equals AJ. So I can do all of these calculations without ever actually having an inverse matrix in front of me. And not only do I save work by doing that, but I also save potential numerical headaches, because it's generally a very, very bad idea to actually compute when you're working with numerical stuff. And when I say numerical in this course, as always, I mean stuff like floating point. If it were exact rational arithmetic, the numerical issues wouldn't be as much of a problem. If I'm working with floating point, I want to make sure I avoid numerical instability or other problems like that, and solving systems of equations does that. Now, you might observe that because I mentioned a minute ago that I seem to save some work by solving systems of equations. So solving this system requires this number of operations, computing the inverse requires this number. But it looks like that gets negated, because I used the inverse 3 times. And that means if I did compute the inverse, sure, it would require more work, but I could recycle it. And you might be wondering, well, doesn't that negate the performance advantage? Perhaps it does. Although it doesn't undo this numerical thing. So we still don't want to use an inverse matrix, even if the performance is equal. Sorry, I guess I forgot about this. There is similarly a derivation of how we could adapt the dual method, the dual simplex method, to not use inverse calculations. I'm not too excited about this. There it is, though, if you need it. If I were to implement these algorithms to avoid the use of inverse matrices, we then call the result the revised simplex algorithm. So that revision that makes it the revised algorithm is actually a sort of practical numerical revision, or maybe a performance revision. It's an enhancement that impacts performance and stability, but not really what the simplex algorithm is fundamentally doing. So up until this slide, or maybe up until this slide here, slide 103, everything we talked about in these 3 parts was just the original simplex method. This is finally, we are now at the revised simplex method. The reason why I would argue that even though maybe the fact that I'm using AB inverse repeatedly makes it look like computing the inverse doesn't have a performance disadvantage, one thing to observe is there are a lot of other tricks we can use to avoid, if I have to solve several different systems of equations with the same matrix. So here I have to solve systems of equations that involve AB inverse over and over again. I don't want to compute AB inverse, but maybe solving the systems from scratch each time takes a lot of work. There are results out of numerical linear algebra that lets me have the best of both worlds. They allow me to, so an example would be what's called an LU decomposition. So I don't want to get into too much detail here, but when you perform Gaussian elimination to solve a system of linear equations, you are implicitly computing what's called an LU decomposition. And an LU decomposition, once you compute it, you can recycle it. So the LU decomposition doesn't depend on any particular vector that you're solving it for. So what you could do, if you don't want to use AB inverse, you could compute an LU decomposition of AB and then recycle it over and over again. So every time you need AB inverse, you could solve a system of equations using an LU decomposition that you'd already computed. Additionally, there are tricks that can be used where if you update the matrix AB, so for example, you perform a pivot which changes the basis, which you might realize only changes one column of AB. It turns out that there is a way of updating your LU decomposition without too much extra work. If you're careful, you can update the factorization by making some small updates. That means that the revised simplex method can give you a lot of other performance advantages by dragging in all these extra results from numerical linear algebra. Now, this is not a numerical linear algebra course, although I really hope somebody wants to talk about that, some grad student wants to talk about that for their presentation. If you're interested in numerical linear algebra, here are some options. So this is not a numerical linear algebra course, but here are some things you could try. One, you could be a grad student in this course and do a presentation about numerical linear algebra. Two, this department allegedly offers a course on numerical linear algebra called CSE 449. You could go ahead and take that course next time it's offered. Disclaimer, the last time that course was offered, I was an undergraduate. So sorry about that. The reason that it hasn't been offered since then is that the last numerical analyst on faculty retired, and that just nobody since then has been able to teach it because they've been too busy teaching other things. You could also, given that that's sort of sad, you can take CSE 490, which is the directed study course, with some numerical linear algebra focus. I think anybody who's studied that at a high level recently has had to do it via a directed study. I would really like it if one day this course gets offered again. And I will admit, I might regret admitting this, I will admit I am strongly tempted to make a play for it. So about a year ago, I'm recording this in mid-June, about a year ago I was recording a lecture for my fourth year course last summer, which was a course on data compression, where inadvertently I began talking about von Neumann and Danzig. And I said, you know, we have this course in linear programming called CSC 445. I wish one day somebody would teach this course again. And then, you know, obviously I found it rather amusing. A year later, I was recording videos also about Danzig and von Neumann because in the meantime, it was me that ended up teaching this course again. Who knows? Maybe that will happen again. I certainly hope that somebody one day teaches this numerical linear algebra course again. So if you're interested in that sort of thing, you can take it. But in the worst case, if that doesn't happen, there are other ways that you can still study numerical linear algebra, not just recreationally. If you're interested in that, come and talk to me. I'm not sure if I have the ability to supervise too many directed studies in the fall this year, because I've got a lot of teaching, but I may be able to supervise them in the spring or next summer or something. So if you want that sort of thing, please come and talk to me about it. I think it's a really interesting topic, and I like directed studies because it lets me learn more about a subject.